Hello everyone and welcome back. So this time we're going over the resolution of a vector. Now you might be thinking, wait a second, this looks just like what we were talking about. This is the parallelogram method. You're trying to call it something new. Well, yes. Yes, there is a parallelogram right here. You can see that, but this is different because previously we were adding two vectors together to get one big vector. This time, we're going to take one big vector and get two smaller vectors. We're going in reverse here. Why do you care about this? Well, maybe you want to figure out what forces are going along this direction, or what forces are going along this direction. And please note, these forces are not perpendicular. That's going to be important later, but for this one, this method, it doesn't actually matter. Okay, so you want to figure out, well, what force is going in either of those two directions. Well, we can use resolution vector to break it up, and it's just the reverse of our parallelogram method. So you're going to draw the parallelogram, just again, but this time instead of knowing the sides, you will know the length of that vector, and most likely its angle. And then you will use angles and identities and all your trig functions to figure out the length of both of the sides of that parallelogram, and then you can solve. So just as a note, this is parallelogram law in reverse. I am taking all my fun trig and I'm doing it in reverse. And we'll do some examples of this towards the end. Okay, now addition of a system of coplanar forces. For everything we do in this class, it's always going to be coplanar, which is amazing because it makes everything so much simpler. When I say coplanar, I just mean that they're all in the same plane and they're all on the screen. There's nothing coming straight at you. It's all right there. In most of our problems, what you're going to be required to do is to break up everything into components. Components along three perpendicular axes, or in this case, probably two perpendicular axes, which is usually defined as the x and y direction, where x is usually horizontal and y is usually vertical. That's not always the case, but many times it's the case. And so what we want is we have some vector f. When we find out what's the component along the x direction, which is usually shown as with the subscript x, or what's the component of that force along the y direction. So if I break it up, what's the component? And you're like, well, isn't this that parallelogram law again? You're just trying to make up new things and call them different things. So yeah, still looks very similar. It's just that in this case, it's a 90-degree angle, which makes everything so much simpler. So remember that 90 degrees right there, 90 degrees right there. So it makes everything easy with your trig. Don't do any really crazy triangles. You can just do law of sines. You don't have to do law of sines. It's just you know one of the angles. Everything's super simple then. And so we're trying to break these up into two components. You're going to be using like cosine of theta and sine of theta all the time. So remember, opposite over hypotenuse is, that's sine of theta. Adjacent over hypotenuse is, that one's cosine of theta. Okay, so based on what you know, you can figure out what you need to get. Okay, and I believe that's where we're going to stop it. Nope, we got one more little thing here. And this is just to show you how you would write that. So we have the f vector right there, and you see we have this I vector and this j vector. Those are just direction vectors. They're unit vectors, so it means that if you multiply a scalar by them, that just tells you what direction it's going, and then the scalar is the magnitude. So they give the direction, but nothing else. They don't give a magnitude. Their magnitude is 1. And then fx and fy, their components, they are scalars. That's just the length of the vector in the I or j direction. So you see that y is connected to j, and x is connected to I. And if we had z, it would be connected to a k vector. Okay? And if we rotate things, things can change. We can choose any x or y axis that we want. That doesn't matter. It won't change. It might change the components and how big they are, depending on what directions we choose. But in the end, their magnitude will still be the same. And when you add them together, they will still be that vector. Okay. I know there's a lot here. This is always easier to see with examples, and I promise we're going to work some at the end. So keep on watching the videos, and we'll get to a few of them at the end, or you can just jump there right now if you want to. So, I'll see all of you next time. Have a good day. Bye-bye.